In my lab of constant velocity with zero net interactions, I chose to study the movement of a small tennis ball across the floor. In setting up to accurately study velocity with no net interactions, the object I chose was a dog toy in the shape of a tennis ball. The ball's mass is 0.056 kilograms, and in order to get a more accurate measurement of a known length, I added a highlighter in the center of the frame with a length of 5 1/8 inches, which converts to 0.130175 meters. I chose not to round any values in this assessment of constant velocity in an attempt to get the most accurate computer model as possible. In the process of recording the video for analysis, the camera was not resting truly level with the surroundings and the translation of motion, so I chose to tilt the axis negative 2.7 degrees from horizontal. The origin of my coordinate system is placed at the center of mass of the tennis ball in the very first frame, which depicts the ball already traveling at a constant velocity. In this case, that's 0.667 meters per second along the negative x-axis, calculated from the difference in the second frame to the first. I chose to keep the standard orientation of the axis aside from the slight tilt to reduce confusion as to if the ball's translation was also along the z-axis. So for understanding the data in this lab, the ball is translating across the negative x-axis and the center of mass is as close to zero in the y-axis as possible. While editing the outline given in VIDLE to produce the accurate computational model, the total net forces was set to zero, being as this is a study of constant velocity. In the graphing of my findings, model versus experiment, we can see that the model constructed did a very good job at predicting the motion in the first 17 frames of the video. In the frames following the 17th, the model and experiment data grow further apart from one another. Looking further into why this might be the case, I came to the conclusion that it is possible that the ball started slowing down in all frames after the 17th, whereas the model depicts constant velocity. Another reason why this may be is that the ball's translation isn't just across the x-axis, but also across the z-axis. Also, the object chosen for this lab was a tennis ball. Tennis balls are covered in a felt-like material which could add to the friction created when the ball rolls across the floor, slightly slowing it down. This particular ball's shape could play a role in this as well. If the ball isn't truly round and has high points and low points in its surface, then this could affect the direction of the ball's velocity. A change in direction would equate to less distance traveled through the negative x-axis in the time interval because some of this energy is now used to translate through the z-axis as well. To investigate which of these possible explanations might be true in this case, I chose to calculate the velocity in the difference between the second frame and the first frame, and the last frame and the second last in the experiment data. After doing this, we can see that the initial velocity is 0.667 meters per second in the negative x direction, and the final velocity is 0.515 meters per second in the negative x direction, showing that the ball is slowing down through a loss or change in velocity. Without being able to plot for the z-axis in this video, it is hard to tell which, if any, or all of these are true. If, however, I was able to set the plot for the z-axis, I would be able to see if the ball's motion translates in this plane. I chose not to apply the y-axis for this because this axis relates to motion traveling up or down and not toward the observer or further away. So given all the tools provided and a small amount of problem solving, I can conclude that the computational model constructed to predict the motion of a tennis ball across the floor does a very good job until the interactions of the ball with the surroundings change or the direction of velocity changes. Thus, the velocity is no longer constant and the equation F net is equal to 0 can no longer be true. Or the direction of velocity changes and must be rewritten for all frames after the 17th. I realize that I could have easily cut the video off at the 17th frame, concluding that the model and experimental data line up perfectly. But to get more out of this lab, I chose not to doctor the observations to match the model. Rather, I chose to keep what I had done and explain why it might be